Welcome to this video. We are in the current videos looking at vectors, and we have already seen that if you have two vectors you can add them. If you have a vector and a number you can do scalar multiplication. And we have also considered the dot product of two vectors, which is incredibly useful if you're interested to compute angles between vectors. Now in this video we will look at yet another operation that you can do with vectors, and that is from two given vectors a and b you can compute something which is their cross product, and that is a vector, and that can be useful for a number of applications again. So let's have a look at the contents for this video. So I will first give the definition of cross product and some examples. Then I will indicate once more the difference between dot product and cross product. Dot product is a number, cross product is a vector. So this one is also called sometimes the scalar product, and this one the vector product. And I will give some properties of the cross product. So let's have a look. First, the definition. So given two vectors a and b, you see that the definition of the cross product is a very strange expression here. So what you do is a2 times b3 minus a3 times b2. That's going to be the first component of this new vector. Then the second one uses the first component of the a vector and the last component of the b vector, and then the last component of a times the first of b, and then with an additional minus sign and here a plus. And then finally the last component here deals with a1 times b2 minus a2 times b1. So let's do a simple numerical example just to get the hang of this. And maybe also to already try and indicate why this is going to be of use for us. So I'm going to pick two vectors. Let's say for A, I'm going to pick 1, 2, 3. 1, 2, and 3. And for B, I'm going to pick 4, 5, and 6. 4, 5, and 6. Now, A cross B, so that's how I pronounce this, A cross B. So it's going to be a vector with three components, just like A and B have. And then for the first component, I have to start with A2 times B3. So A2 is this 2 and B3 is this 6. So we get 2 times 6 minus. And then we have the third component of A times the second component of B. So this 3 here times this 5 here. So we get minus 3 times 5. So you see that for the first component of the cross product, we use not the first components of the A and B vectors, so the second and third components of the A and B vectors. Second component, minus A1 times B3, so this minus 1 times 6, minus 1 times 6, plus, and then we get A3 B1, so that's 3 times 4. And then finally for the third component of the cross product, we use A1 B2, so 1 times this 5, 1 times 5, minus, and then here we get A2 times B1, so A2 B1, 2 times 4. 2 times 4. So you see that we get the vector. Let me make a little bit of space so I can put it behind here. So we get the vector equals, so we have 12 minus 15, that's minus 3. We have minus 6 plus 12, that's 6. And we have 5 minus 8, minus 3. So this is just the definition of cross product. You take two vectors and you compute a third vector. There is no understanding here. This is just a mathematical operation. Why this is useful, or what we can do with this cross product, that's going to come up next. So I'm asking a little bit of patience of you to show you that this makes sense and can be useful. Why it can be useful, I'm already going to make a little bit, I'm going to teach you a little bit why this may be useful. What I'm going to do is I'm going to compute a dot product with a cross B. So the A vector is 1, 2, 3. And I'm going to compute the dot product that we have seen in the previous video with minus 3, 6, minus 3. So what we get is minus 3 plus 12 minus 9, which is 0. So if you think back, what did that mean? You take two vectors and you compute that dot product. That tells you something about the angle between them. If you find that dot product to be 0, you know that they are perpendicular. They make a 90-degree angle. So what we find is that A and the vector A cross B are perpendicular. So they make a 90-degree angle. If you would compute the dot product of B with A cross B, you would find the same thing. So I invite you to do so. I'm just going to write the conclusion here. So we also have that B and A cross B. They're also perpendicular. So apparently what this dot product arranges, what this cross product arranges, if you take two vectors, A and B, you compute their cross product, A cross B, then you find a vector that is perpendicular to both A and B. So if you think a little bit about what that means, we are in space. I have a vector A. I have a second vector B. And then with this cross product, I can make a vector C that is perpendicular, orthogonal to both of them. So if you have a little bit of visualization powers, if you have a vector A and B, then they span a plane. There is a plane that goes through these two vectors. And what you create with A cross B is a vector that is perpendicular to the whole plane, to every vector in this plane. And we will be using that in what follows. Okay, so just a bit of naming. Cross product is also called a vector product because it gives you a vector. And A cross B, so this vector product is also a vector. So just for emphasis, we have seen in a previous video that the dot product is a number, which is written A dot B. And now we have the cross product that's new, and that is a vector. So A cross B is a vector. Great. Okay. So this is what we have already seen in the numerical example that I showed you. So if you pick any two vectors and you compute their cross product, you find a new vector that is orthogonal to both A and B. So here is in the picture, I have an A vector, I have a B vector, and then A cross B is perpendicular to both of them. Now, you may visualize and think that if you have these two vectors, so I have these two vectors A and B, and then I find a vector that is perpendicular to both, well, this direction is not unique, right? I could also have picked this one pointing down. And what you can show is that if you swap order, if you do B cross A, that you find that vector. So this looks a little bit like a product, but you see that if you change the order, that you get a minus sign. So if you have two vectors and you compute their cross product, the order is important. With A cross B, you find this black vector. With B cross A, you find this green vector. And if you want to know which direction the cross product has, you can use what is called the right-hand rule. And the direction is as follows. So if you have two vectors A and B, and if you let A be your index finger, if you let B be your middle finger, then you see that you get a construction where your thumb is perpendicular to them, and A cross B is the direction of the thumb. Okay, so you have to use your right hand, otherwise it points the other direction. Yeah? And you can see here the illustration with A, B, and A cross B. Now, what you may remember is that we could express the dot product as length A times length B times the cosine of the angle theta between two vectors. We have something similar for the cross product. Of course, the cross product is a vector, but if you look at the length of this vector, then it's the length of A times the length of B and now the sine of theta. And what you then find in particular is if you have parallel vectors. So parallel vectors, again, that means that B is a multiple of A, and it can be that B and A point in the same direction as we have here, or they can point in opposite directions, which means that their angle is pi. In both of these cases, you see that the sine of theta equals 0, because the sine of 0 is 0 and the sine of pi equals 0. So apparently in these cases where A and B are parallel, we see that their cross product equals 0, the length of the cross product. So the cross product itself is 0. So we put that here as a corollary, as a consequence of the theorem, that if you have parallel vectors, it means that their cross product is the all zero vector. If the length of a vector is 0, it means that the vector itself is the 0 vector. And you can also use that the other way around. So if you take two vectors and you compute their cross product and you find it to be the 0 vector, then you know that they are parallel vectors. So either they point in the same direction or they point in opposite directions. Or one of them is the all zero vector, but that's not such an interesting case. So let's look at two simple applications of the cross product. One of them is if you have a vector A and a vector B, that you could look at the parallelogram that is spanned by them. So here we have A plus B. And now if you would like to know the area here, so that's the blue region, then the general formula is that the area is the length of the base times the height. Well, the length of the base, that is simple. That's the length of this vector here. So we have that base equals the length of A. For the B vector, what we need is the height. Sorry, for the height, what we need is the component of the B vector. So we need the length of this part. So we can decompose the B vector in a part along A and a part orthogonal to that. And if we have this length here of this vector, then we know what the height is. So how can we do that? The height is the the length of B times the sine of theta, where theta is the angle between A and B. So we know that the area is length A times length B times sine of theta. Now, if you just give me vectors, I don't know their angle. So ideally, I would like to have a formula without the angle, but I recognize this thing precisely as the length of the cross product. So apparently, the area of this parallelogram here equals the length of the cross product. So if you give me two vectors in space, I just compute their cross product, take the length, and then I know this area here. And you can imagine maybe that if you have, for instance, computer games, that this is something that you're interested in to know, or for visualizations. So this is extremely useful. And here it is as a theorem. So if you have two vectors in space, then the area of the parallelogram is simply the length of A cross B. There is also a version of this where you have three vectors, and then you have a parallelepiped. I'm only going to say that once. So we have a vector A, we have a vector B, and we have a vector C, and together they span something that is a bit like, well, how would you say it? It's a bit like a cube, but not all the sides need to be equally long, and you can just hit it. So just three vectors, and they span a volume. And for this volume, we can also find an easy formula, because the volume is the area of the base. Well, the base, that's the parallelogram that we just covered on the previous slide. So we already know that's the length of A cross B times the height. So what is the height here? Well, let's make an illustration where we look in the plane through C and A. So we take this C vector, we take this A vector, and then we look at the plane that goes through them. So then we have A cross B and we have C. And what we should have for the height is the length of the projection of C along A cross B. And we have seen in a previous video how we can compute that. Because if we take the absolute value of the component of C along A cross B, this was the component, so I just put absolute value signs there. And apparently this is the height. So we now know the volume, because the volume is the length of A cross B times the height. And you see that it even simplifies, because there is also an A cross B length here and it drops out. So altogether, what we find is if you give three vectors in space and you want to compute the volume that is spanned by them, so what you see here, the volume inside this cube-like thing, that you do the cross product, then a dot product, and then you take the absolute value, because a volume needs to be a positive number. So incredibly useful here if you want to compute volumes in space. And again, if you have like computer games, then you have objects in the computer game. They're usually built out of many of these kinds of shapes. And if you need to know the volume, you just add them together. And this is a very easy way to do so. So what we have seen in this video is the following. We have seen how you can define the cross product of two vectors. We have seen how this cross product gives you a new vector that is perpendicular to the two original ones. And we have seen two applications. One is if you want to know the area of the parallelogram spanned by two vectors, then you can find an easy formula for that. Or if you want to have the volume of three vectors that is being spanned, the volume that is being spanned in 3D by three vectors. That wraps it up for this video. I hope you enjoyed it, that everything was clear. Otherwise, let me know, and I'll see you in the next video.